because the derivative of constant equals 0. Maybe sometimes, we are given an initial condition, then we can solve for this c. So if you give me any point for this function, then I can solve for this c. All right, so that's the process. So let's go through definitions. A function, capital letter F, is called an antiderivative of little f on an interval I if derivative of capital letter F equals to the little f. Okay, for all x in the interval. So some examples here. If little f is x squared, and we'll use the antiderivative power rule. So big letter of capital letter F is 1/3 of x cubed plus c. All right, so we'll write 1/3 of x cubed. Hold on, this is giving us plus c. All right. So part of it is 1/3 of x cubed. That's true because 1/3 times 3. When we take derivative of this, we do get x squared. But then we have to add c to it. We have to add a constant to it. All right. So it should be 1/3 of x cubed plus c. Let's see this theorem. If f is an antiderivative of little f on an interval, then the most general antiderivative of f is this. All right. It's an antiderivative plus a constant. C is not constant. We don't know what kind of constant it is. We just add a c to it. Okay, let's see this one. Example 1. Find the most general antiderivative of each of the following functions. So if f equals sine x, right? So we think whose derivative is sine x? Right, we write this. We write a derivative. The derivative function is sine x. Then, so when we take derivative of what function, we get derivative to be sine. That's cosine, right? Cosine is negative. That's negative cosine. So our original function has to be negative cosine because the derivative of cosine gives us a negative sign. So negative sign gives us positive sign. So it's the opposite thinking. All right, we think, okay, whose derivative is the sine? Negative cosine. But if x raised by n, we think whose derivative is x raised by n? That has to be x to the power n plus 1. But then divided by n plus 1, right? Because if we take derivative of this, x raised by n plus 1 divided by n plus 1, we get n plus 1 x raised by n divided by n plus 1. N plus 1 here to be 1. X raised by n. So think, okay, we have opposite thinking. Whose derivative is x raised by n? And this process, what we'll call later on, is called power rule for antiderivatives. So let's look at 3. So x raised by negative third. We think whose derivative is x raised by negative third. Right. What we do is we do something called antiderivative of power rule. It's exactly this one. It's exactly here. All right. So f of x equals to now x raised by negative 3 plus 1, which is negative 2. Then divided by negative 3 plus 1, which is negative 2, divided by negative 2. We simplify, we get 1 negative 1 over 2x squared. We will call this step antiderivative power rule. So what do? We add 1 to the exponent. We add 1 here. Let's look at C, for example. We add 1 to the exponent. You see, it's the opposite to when we take derivatives. When we take derivative, we subtract 1 from the exponent. But for antiderivative, we add 1 to the exponent. Then we divide it by the new exponent. -3 plus 1 is -2. Then we divide it by -2. Okay, so we add 1 to the exponent. We divide it by the new exponent. Then, of course, we add c to it. Right? We add a constant to it. We add a constant to it. So this is called the power rule for antiderivatives. Okay, here we have some, this is true. If the scalar of a function is the scalar of the original function, right? If the derivative function is the sum of two functions, it's the sum of, its derivative, antiderivative. Its antiderivative is the sum of the original functions. This is the power rule. X raised by n, n not equal to -1, right? Because if n equals to -1, we have a -1 plus 1, we have x raised by 0. That gives us 1. It doesn't work. So if x equals to the -1, let's try to remember this one. So ln of x, ln is log base e, right? So natural log. If the function equals to, let's see, f of x equals to ln x, then it's a derivative. Let's follow the book. Use the big left this section. So it's a derivative. It's a 1 over x, right? So this book didn't really talk about this, but let's remember this. So log x, its derivative is 1 over x, or x raised by -1. So in here, let's add 1 here. So if it's x equals to x raised by -1, and let's add 1. So it's a derivative, it's an antiderivative. Its antiderivative is ln x, right? ln x. Also, we didn't talk about this one, I think. If f of x equals to e to the x, then f prime of x is itself. The e term, when we take derivative, is always itself. Right? Maybe sometimes the e raised by x squared, then we have to do chain rule. We will get the derivative to be e to the x multiplied by 2x. All right. But in general, the log function derivative is 1 over it. But if inside the log is x squared, then we have to apply chain rule. But ln x derivative is 1 over the x. E to the x derivative is e to the x. So let's put over here also. So if here we have e to the x, its antiderivative also e to the x. So this is the only function the derivative is itself, the e term, except the chain rule part. If this is e raised by 2x, we will have e raised by x, then multiply by 2. All right, let's see here. If the function is cosine, if the derivative function is cosine, it comes from sine, right? Original function, the antiderivative is sine x. If the derivative function is sine, antiderivative is negative cosine. If derivative is secant square, antiderivative is tangent. If derivative function is sine secant tangent, then antiderivative is secant. Well, we can think this way. This way is always easier to think, right? Derivative of sine is cosine. Derivative of negative cosine, that's sine. Derivative of tangent is secant squared. Derivative of secant is secant tangent. But now we're thinking antiderivatively. So we go this direction, all right? Okay, let's see example 2. So G prime is given as 4 sine x plus this. Let's try to find all functions of G. That means a family of functions. That means add C to it in the end. So antiderivative, right? So whose derivative of sine is negative cosine, right? Negative cosine. The scalars we just leave on the side. The 4 is a scalar we just leave on the side. So sine antiderivative is a negative cosine. Then here we can use power rule. Maybe you can simplify this a little bit, right? 2x raised by 5 divided by x, 2x raised by 4. So simplify the function a little bit. We have 4 sine x, 2x raised by 4, then negative square root of x divided by x, that's negative 1 over square root of x, or negative x raised by negative half. We want to write as a polynomial like. X raised by negative half. Now we use power rule for those two. Power rule for antiderivative is saying add 1 to the exponent. Now this becomes x raised by 5. Then divided by the new exponent, 5 divided by 5. So we have this. Simplify this, we have 2 over 5 x raised by 5. Same thing for this one, for this term. Add 1 to the exponent, negative half plus 1, positive half. Then divided by half. Divided by half is the same as multiplied by 2. Right? Divided by half. So we have x raised by half divided by half. Then we simplify this, we get a minus 2 radical x. Then we add constant family to it, add c. So the antiderivative is a function, is a family of functions. If you have any questions, stop me anytime. So this way we always use in differential equations. We try to solve differential equations. Okay. In the equations, we have differential terms. Let's see this one. This one we have actual condition, right? We have derivative function x, square root of x, we can write as x raised by 3 over 2. Then we have an initial condition. So we're given a 1 point, or given a point 1, 2. So first, the derivative function we can write as x raised by 3 halves. Then we apply power rule. We add 1 to the exponent. It becomes 5 over 2. Then we divide by 5 over 2. Dividing 5 over 2 is the same as multiply 2 over 5. Right? Multiply by its inverse. So we have 2 over 5 x raised by 5 over 2 plus c. Now we're given 1 point. This point is saying x value is 1. We substitute x into 1. Y value is 2. We substitute the y value into 2. So that becomes 2 over 5 multiplied by 1 plus c equals to 2. Now we can solve for c. So c equals to 2 minus 2 over 5. Well, 2 we can write as 10 over 5. 10 minus 2 get 8. So c equals to 8 over 5. Then we plug into c. So the function we can write as 2 over 5 x raised by 5 over 2 plus 8 over 5. How did I get 5 over 2? Okay, 3 over 2 plus 1. We add 1 to the exponent. Three over 2 plus 1. 1 is 2 over 2, right? We need a common denominator, so we get a 5 over 2. All right. Okay, then we can write this way. But usually we don't write the answer. We do not write x raised by a fraction power. We would write this as equals to 2 over 5, 2 over 5. Then x raised by 5 over 2, we can factor out x squared, right? We can write it as x raised by 4 over 2 plus 1 over 2. 4 over 2 is 2, so we can write x squared square root of x, then plus a over 5. Right, we want to write this way. So 2 over 5, right, that's a scalar. Then the variable term will have an x squared square root of x plus a over 5. All right, let's see example 4. Example 4, we're given second derivatives. So second derivative is 12x squared plus 6x minus 4. Then we're given 2 points. We're given 0, 4, 1, 1. All right, so we want to find original function. So let's find the first derivative. So second derivative is, let's find the first derivative. We'll apply power rule for antiderivatives. So we leave the scalar 12 on the side. So I see x squared. What do? We add 1 to the exponent. So add 1 to 2, that becomes 3. X cubed, then divided by 3. So I have 12 times x cubed divided by 3. Here, leave 6. 6 is scalar, leave on the side. We have x raised by 1. Then we add 1 to 1, we get x squared, then divided by 2. Minus 4, this is minus 4x, right? Derivative is a minus 4. Original function has to be minus 4x. Then we add a constant term. We simplify a little bit, so we get a 4x cubed plus 3x squared minus 4x plus c. So this is our first derivative. Now from first derivative, again we apply antiderivative power rule. So we take these 3 terms, leave the scalar on the side. We add 1 to this exponent 3, get 4, then we divide it by 4. So we get x raised by 4 divided by 4. Leave 3 on the side, we have the exponent 2, add 1 to 2, get 3, then divided by 3. So we get second term, we get 3 times x cubed divided by 3. Minus 4x, this x raised by 1, we add to it, 2, then divided by 2, negative 4 times x squared divided by 2. C, derivative of c, antiderivative is cx. Then we add another constant. And this constant we write in different name. We write as a d. So now simplify a little bit. So we get x raised by 4 plus x cubed minus 2x squared plus cx equals to d. All right, so this is our function. Now let's plug in the 2 points. So 1 point is saying f of 0 equals 4. So let's plug in 0 into the function. 0, 0, 0, 0. So we get d equals to 4. Right? So plug in 0 for all x, we get d equals to 4. Then we have another point, 1, 1. So let's plug in 1, 1, 1, 1. So we have 1 plus 1, 2, 2 minus 2, 0. Then we have c times 1, that is c. c plus 4 equals to 1. So we get this. C plus 4 equals to 1. That means c equals to negative 3. So we substitute c and d into f of x. So we get the original function to be f of x to be x raised by 4 plus x cubed minus 2x squared minus 3x plus 4. Okay, this is basically the steps how to, given, we see what's the difference. The example 3, we're going to first derivative, right? We're anti-first derivative. We're given 1 point, and we're able to find one and only one function for that. As an example, we're given second derivative. If we want to recover to the original function, we need 2 points. So as you can imagine, if we have the third level of derivative function, and if we find one specific function, we would need 3 points, right? Because when we anti-differentiate, we will have 3 different levels of constants. So we need 3 points. All right, we can always take a derivative of this to check to see if we did it right? We take a derivative of f to see if we get, then we take a derivative of f prime to see if indeed we get this second derivative function. All right, let's see example 5. This is application. This application is saying a particle moves in a straight line and has acceleration given by this. Acceleration, if we remember, that's our v prime, right? V prime of t. Acceleration. Its initial velocity is v of 0 equals to -6. And its initial displacement is s of 0 equals to 9 cm. So we're given, you see, 1 point for the velocity, right? Velocity, what is the velocity? Velocity is the displacement derivative. So let me write here. So basically s v of t equals to s prime of t. And a of t equals to v prime of t, or equals to s double prime of t. So that's this relation over here. Acceleration is a derivative of the velocity. Okay, or second derivative of the displacement. Velocity is the derivative of the displacement function. All right, so having this relationship, let's antiderivative. So a of t we can write as a v prime of t, right? That's 6t plus 4. Well, let's apply power rule for antiderivatives. So we want to recover v of t. So v of t, t is t raised by 1. So 1 plus 1 is 2 divided by 2. So t squared divided by 2. And simplify that, we get 3t squared. Antiderivative 4, that's 4t, then plus a constant term. So velocity function is 3t squared plus 4t plus c. Now we're given a point, right? V of 0 equals -6. So plugging in 0 for t, so t, we get c equals to -6. So now we get a velocity function. So that's 3t squared plus 4t minus 6. Right, so I have this. Now v, the velocity function, is a derivative of the displacement. So let's antiderivative of v of t. So antiderivative of v of t, we get s of t. We still apply power rule. Add 1 to 2, we get t cubed divided by 3. Add 1 to 1, we get t squared divided by 2. Antiderivative of -6, that's -6t. Then plus a constant. Let's call this constant d to differentiate from, distinguish this from c. So simplify this, we'll get a t cubed plus 2t squared minus 6t plus d. Now we have another point, right? We have 0, 9 for displacement function. So we substitute 0 for t, that equals to 9. 0, 0, 0, d equals to 9. So that means d equals to 9. So we put a 9 into d. We get a displacement function to be t cubed plus 2t squared minus 6t plus 9. All right, that's how we use this antiderivative in applications. Any questions? I'll keep going. So let's see this one. A ball is thrown upward. So if we throw a ball upward, we make a downward parabola with a speed of 40a from the edge of a cliff. Right? Oh, okay. The cliff 432 feet above the ground. Find its height above the ground t seconds later. Okay, so we need to find a function in terms of height. when does it reach its maximum height? Right? So imagine we have someone. So this is a cliff. Right? Someone standing here, toss a ball upward. And then we know the height here is 432 to the ground. So let's see. Let's think this is as a ground. So this is 432. And the speed of tossing this up, which is v prime, which is v speed is velocity, v of t equals to 48. Right? We just think about the average speed. For thrown upward with a speed of 48. So when does it reach its maximum height? Right? Let's say we want to find this maximum height. And when does it hit the ground? When does the height be 0? So let's see. We assume the motion is vertical and we choose the positive direction to be upward. And the time t, the distance above the ground, is s of t. And the velocity is s prime of t equals v of t is decreasing. Therefore, the acceleration must be negative. And then when we have acceleration equals to dv over dt, where v prime, dv over dt means v prime equals to negative 32. Where does negative 32 come from? Changing in v, dv, this example is coming from somewhere. Oh, it's from here. Oh, no wonder. Okay, the question actually started from here. The object near the surface of Earth is subject to gravitational force and produces a downward acceleration denoted by g. For motion close to the ground, we may assume g is constant, its value being about this much, or 32. Okay, we use this constant. 32. Okay, all right, that's where 32 comes from. All right, because it's decreasing, so we use negative 32. So acceleration is v prime. So we antiderivative, we get a v of t. We antiderivative this function, right? So that's negative 32t plus a constant. And we're given a 1 point, right? 0, 48. So v of 0 equals 48. And this gives, so 48 equals the negative 32t plus c. So we solve for c. Well, this 32 times 0 is 0, so c equals to 48. So get a velocity function. Velocity function is negative 32t plus 48. Then, so when is maximum? Maximum means we take a derivative, we set to be 0, right? So v of t, that's v of t equals 0. Well, v of t is s prime of t. S prime of t equals to 0. So v of t equals 0, set this one to be 0. So solve for t equals to 1.5. Right? Then we antiderivative of v to get s. So we add 1 to this t raised by 1. So t squared divided by 2 times negative 32, get negative 16 t squared. Antiderivative 48, we get 48t, then plus a constant. Now we have the initial height, right? 432. So we get 0, 432. We use this point. So 432 plug into this function, it equals to, the first term becomes 0, 48t becomes 0 plus d. So d equals to 432. So put it back into s of t. So s of t equals negative 16t squared plus 48t plus 432. We see it's a downward parabola. Right now, we want to find out the second question. The second question is, when does it hit the ground? So that means when does we make s of t 0? So s of t equals 0, just set the function to be 0, we get a quadratic equation. Then we can solve for t. Solve for t, this is not factorable. It's not factorable. We use quadratic formula. So we have negative b plus minus square root of b squared minus 4ac. We simplify, get this. We get 3 plus 3 square root of 13 divided by 2, or 3 minus 3. We see 3 minus 3 square root of 13 will be negative. We don't measure time negatively, so we reject the negative value. And 3 times, so 3 plus 3 square root of 13 divided by 2 is approximately 6.9. So after 6.9 seconds, the ball will hit the. So this is example also using an application. Any questions? All right, so let's keep going. Oh, let's do some exercise. Find the most general antiderivative of the function. All right. So let's try. So basically seeing this f here, so think f here equals to f prime, all right? And find f, find the big letter f. So the section uses different notations for derivative, so don't get confused with that. So here, thinking about each f, g, h as a derivative function for the big letter, for the capital letter, all right? To find the capital letter function. So let's try, excuse me. Let's try 1, 3, 7. So 1, 3, 7, 7, 3, 1, 9, 10, 8, 14. Okay. Antiderivative, right? Thinking backwards. Thinking whose derivative is that? Or use the power rule. Okay, need more people to have 2, 7, 14. Okay, now I have 3, have 9, 2, 3, I have 10. Okay, great. Anybody wants to do 1? 2. Right, Emily, 2 is not, but the 1, do you want to try 1? I think we're only missing 1. All right, let's start. Great. Let's see. We start with Henning. Henning 14, then Emily 2 or 1. Emily 1. Let me make you guys presenters. Oh, Andrew want to do 1? Sure. Let me make you presenters. Malika is already presented. You know, it'll be great for those people you haven't presented much yet. Okay, Rudy. Let's see who else. Okay, I think I made all of you presenters. All right, let's. Okay, whoever is ready, let's go ahead. What's going on? Anybody's ready? Okay, so Henning, great. We cannot hear you yet.
Okay, can you hear me now?
Now we can hear you. Yeah.
For this question, we have to find the antiderivative. So I added +1 to the theta to the second power. And then you know that secant squared theta is equal to, well, like the antiderivative is 10 of theta. And then you do plus c. And after you add 1 to the theta, you get theta to the third over 3. So then that would divide into 2 theta to the third minus 7 10 theta plus c. That makes sense.
Great. Yeah, make a lot of sense. But only the notation, this little f, right? You started with a little f. Oh, yes, you did. It's little f, right? You apply power rule, you apply the trigger rule for antiderivatives, you add a constant c, you simplify. Perfect. Perfect. If anyone has any question, so feel free to ask. Great. Thank you, Henning. Next one. Okay, looks good.
Can everyone see the question?
Yeah.
Okay, so we're asked to take the derivative, the antiderivative of g of t, which is equal to 1 plus t squared over radical t, which is the same thing as 1 plus t squared over t to the 1/2. And so if you simplify that out further, you get t to the negative 1/2 plus t to the 1/2 plus t to the 3/2. So you take the antiderivative of each. So t to the negative 1/2 plus 1, and it would equal to t to the 1/2, and then you take the exponent and divide the whole t to the 1/2 by the exponent. So then you get t to the 1/2 over t over 1/2, and then which equals to 2t to the 1/2. And then you take the antiderivative of t to the 1/2, and you get t to the 3/2 over 3/2, which is the same thing as 2/3 times t to the 3/2. And then you take the antiderivative of t to the 3/2, which is the same thing as t to the 5/2 over 5/2, which is equal to 2/5 times t to the 5/2. And so altogether, the antiderivative of g of t would equal 2t to the 1/2 plus 2t to the 3/2 over 3 plus 2t to the 5/2 over 5 plus c. And
Okay.
it told us to check the, oh, sorry.
It's okay. Yeah, remember I said for the final answer, let's not leave the fraction exponent
Okay.
because that's considered as not simplified. Let's say t raised by half, right? We would rather write a 2 square root of t.
Okay.
Okay, so can you quickly fix this answer for now?
Should I write it on the screen?
You don't have
or...
just to speak. So the first one I did for you. So 2 square root of t, right? What's the second one?
Yeah. Plus 2 and then radical t to the 3rd. And then over 3. Or
So
it's the same thing as 2/3 times radical t to the 3rd.
No, the second term will be 2 over 3. That will be a scalar, right? And for the variable t, so what's t? So t raised by 3 over half. You can
It's
write
the
as
same thing
what?
as radical t to the 3rd, which is...
Right, or we can simplify because radical t to the 3rd is not simplified. We would write a t radical t.
Okay.
Does it make sense? Because 3 over 2
Yeah.
is 1 plus half. Okay, so you do the third one.
It's going to be 2/5 times t squared and then radical t.
Perfect. That's it. Okay, so next time leave that one as answer. All right. Okay, great. Anybody has any question? Okay, thank you, Julie. Next one. Three. Okay, Malika, 3.
So to find the antiderivative, I use the power rule. So the antiderivative of 7x to the 2/5, the power of 2/5, will be 7x to the power 7/5 divided by 7/5, because what you do is you add a 1 to the exponent and then divide it by that. And then for 8x to the power of -4/5, I did the same thing. And then I got the antiderivative. I got 8x to the power of 1/5 divided by 1/5. And then we need to add a constant, so plus c. And then I simplified by using KCC, like keep change. I divided it, and then I got f of capital F of x equals 5x to the 7/5 plus 40x to the power of 1/5 plus c.
Okay, you probably didn't listen my talk with Julie. I asked her to make corrections about her answer. So I will do the same thing. I ask you to make correction about your final result because when a variable is raised by fraction, we consider as not
Oh,
simple.
add a radical.
That's right. You read in a, with the power and index. So how would you fix this?
So it would be 5 times the 5 of radical x to the power of 7.
Right. Radical with the index 5, right? 7.
Yeah,
But
yeah, with index 5.
but then it's also not considered as not simplified because the power is bigger than the index. So 7 over 5 you can write as 1 plus 2 over 5.
1.
Right. So x raised by 1, x raised by 2 over 5. So the first term, I'll do the first term for you. The first term you can write as 5x. Then with radical 5 of x squared. So the first term is 5x. So the index is 5x squared. Let's see if this makes sense for you. You see x raised by 7 over 5. 7 over 5 can be written as 1 plus 2 over 5. Right? What's x raised by 1? Just x, right?
Yeah, just x.
What's x raised by 2 over 5? That's
So
x
it would be,
squared,
yeah, index of 5.
index 5 with power 2. Make sense?
Yeah.
Right. So this is considered as a simplified version. Okay. So why don't you do the second term?
So it would be 40. Sorry. So would it be 40x index of 5x to the radical x?
Not radical x, right? You just, if you see radical, this is 40. If you use the word radical, that's the index with 5. If you see 1, right, index 5, radical index 5, x, right? Yeah, okay, because the power just 1. The power just 1, we don't have to write it. The index, the denominator is the index. Okay, so you write this way. All right, okay, thank you. So this is Malika. Next one.
Professor, I think I'm next, right? I'm doing number 9.
Okay.
All right, so we're given 2 sine of data minus secant squared of data. So we know that the antiderivative of sine of data is negative cosine of data. So you could write, and then we know that secant squared, the antiderivative is tangent of data. So then we could write 2 times negative cosine of data minus the tangent of data, and then we would add a c to put in the general form.
That's right. Okay. So we have a negative 2 cosine data minus tangent data plus c. All right, let's see. Anybody else? Okay, Noella. Noella, we cannot hear you. Noella, I see your answer is right, but I just cannot hear you. So I see no other red. No other red 10, right? It's 10. Oh no. Anyway, I think anybody has any questions?
I apologize, Professor. I had an internet connection.
It's okay. You want to show it now?
Yes, I can.
Okay. Yeah, go ahead. So basically, while we're waiting for her, okay, you go ahead.
Are you able to see it now?
Yeah.
Okay, so for this question, we're given f of t equals 3 cosine t minus 4 sine t. And since we know that the derivative of sine t is equal to cosine t, we know that the antiderivative of 3 cosine t has to be 3 sine t. And we apply the same knowledge to cosine t. The derivative of cosine t is negative sine t. And the derivative of negative 4 sine t would be 4 cosine t. So after we put it together, capital F of t would equal to 3 sine t plus 4 cosine t plus c.
All right. Okay. Looks great. All right. Thank you. Thank you. All right. So let's talk about. So we're going to. Oh, okay. We have one more. Yeah. Go ahead. Who's this work? I cannot
it's
hear.
mine, Angel.
Oh, Angel. Go ahead, Angel.
Okay, so we are given derivative of f of x equals 1/2 plus 3 over 4x squared minus 4 over 5x cubed. And to find the antiderivative, we use the power rule for antiderivatives. So the antiderivative of 1/2 is 1/2 x, and to find the antiderivative of 3 over 4x squared, the 3 over 4 will remain, and then we add plus 1 to the exponent of x. So x squared plus 1 is x cubed, and then divide that by the exponent that we got over 3. And then the same thing for the negative 4 over 5x cubed. And then we add c. So the final answer will be 1/2 x plus 1 over 4x cubed minus 1 over 5x to the 4th plus c.
Great. Yes. All right. Thank you, Angel.
Thank you.
Thank you. Anybody else? I think we did all right. Okay, I'm going to talk a little bit about our new material. So we talk about, remember in the very beginning I said this class only covers 3 things. Limits, derivatives, and integrals, right? So far we only left with only one thing, integrals. So the antiderivative is a precursor for integrals. Oh, I may leave you some exercise. Let's see. You know, actually it's okay, because all these antiderivatives is just help us go into integration. So let's talk about integration today. I have like about 15 minutes. So integrals. What does integrals mean? You think about integrals as infinite sum, all right, for the name of it. Whenever you see this integrals, you think about this as an infinite sum. Just keep adding things, okay, infinite many. You're adding infinite many terms. That's what it means, integrals. All right, let's see. How do we apply this in math? Let's see, in math, we have a formula to find area of a rectangle. We have a formula to find area for a triangle, right? If you give me, you know, some gun like this, right? Some shape like this, I can divide it into triangles. I can measure the height, then find each area of triangle, then add them up. But what if you give me a shape like this, right? Let's see the figure 1. if you give me a shape like this with one side, it's not straight, right? With all those shapes here, I have a sides, all the sides are straight lines, so I can find the area of them. But if you give me a shape, you know, one side is not straight, one side is this curvy. So how I'm going to find area of this such shape? So we use mathematical idea, right? We think, okay, let's put this shape in the coordinates, and the one side I can put on the x-axis, and the other two sides are straight. Also, I can think is from one point of x to another point of x, which is a function value, right? This point, the y value is a function of f of a. This is f of b, and the not straight side I can consider as a function, right? You see this, I treat this as a function. So this is my f of x. And here I have a f of a. Here I have b f of b. So now how do we get an area of this? We want to approximate. We can cut this into different pieces, right? We can cut into half, then we can cut into quarter, here into quarter. If we want to do more, if I cut into half, maybe I have somewhere here. Okay, let's talk about this one. Same thing, right? If I have this a shape like this, I can treat one side as a function. I can treat one side as a function. Then I can cut this. I can cut this shape into different parts equally. If I cut into 4 parts, right? I have 4 parts. I cut this into half, then I cut it into quarter. So I have 4 parts. Then I can evaluate like this. I can approximate the first one as a rectangle, the second one rectangle, the third one rectangle, the fourth one rectangle, right? You may say, okay, this approximation is a lot more than the shape, than the true area, right? Because you see this is not, this is the extra area. This is the extra area, and this is the extra area. This is the extra area. So what we can cut into more pieces. We can cut more pieces to be more precise. Or another way, so here we're taking y value on the right-hand side, right? We're taking this value on the right-hand side, so we make this. We take value on the right-hand side, we approximate like this. Or we can take a value on the left-hand side. The left-hand side will be 0, so I don't area of this. And the second one, I take the left-hand side and mark a rectangle this way. I take the left-hand side and mark the rectangle this way. I take the left-hand side and mark the rectangle this way. The problem is this is too much smaller than the real area, right? Because this is not covered, the empty spot is not covered, it's not calculated into it. This not calculated into it, this not calculated into it. So we can cut into more pieces, right? We can cut into A pieces. We can use the left point for the y value. We can use the right point for the y value. Right, so we can choose different points to approximate. Some people even choose the middle point to approximate. Or we can cut into more pieces, right? We keep cutting, we keep cutting them to be more precise. And the integral idea is to keep cutting into infinite many. So what does that mean? That means this. That means we take a limit. Then let how many pieces? How many pieces is n? If we cut it into n pieces, we call n, right? And each one from 0 to 1, each one will be 1n. Then we take a limit. We let this n go into infinity. So that means we want to cut these pieces into infinite many pieces. So let's see what's the idea into this. Let's see this example. So this example, we want to evaluate this, the area of this. So what do we say? We put on the coordinates, right? That's from 0 to 1. We mark the bottom from 0 to 1. And this side of curvy side is a function of x squared. Then we know this point, 1, 1. So how do we do that? Let's cut it into n pieces. Let's cut it into n many pieces from 0 to 1. So how do we calculate each rectangle? Then let's take a let's take the right hand side value, right? So this one, the first piece will be from 0 to 1/n, right? 0 to 1/n. Then what's the y value? The y value would be f of n minus 1 over n, which is 1 over n squared. So this is right hand side. So pick the right hand side. Right? We pick the right hand side as y value as the height for the rectangle. Right? See this? We can pick the right hand side to mark a rectangle, or we can pick the left hand side. The left hand side of f of this point, right, to mark the rectangle. So this example is to pick a right hand side. So the first rectangle would be 1 over n times f of 1 over n. F of 1 over n, which is 1 over n squared. The second one, right, the second one is also 1 over n. So each width of the rectangle is 1 over n. The only difference is the height. The height is f of that, right, which is the square. So what's the x value for the second one? The second one is 2 over n, right? The x value is 2 over n. So it's 1 over n is the width, then times f of 2 over n. F of 2 over n is 2 over n squared. Now let's see the third piece of rectangle. The x value would be from 0 to this point. X value would be 3 over n. So 3 over n. So the y value, the x value is still, the width is still 1 over n, but the y value is f of 3 over n, which is 3 over n squared. So on and so forth. The last piece, right? The last piece, we still have 1 over n, the width. What about the height? The height is f of 1. The last point, f of 1. We just get 1 squared, or n over n. So that's how we come up with this approximation. So Rn, why we call this R? We call this process called Riemann sum. Let me see if I can find the name. Riemann is a name. Riemann is a great German mathematician, and his contribution to our society is humongous. So he formed something called Riemann geometry, Riemannian geometry. Essence stands, relativity theory. Without Riemann's geometry, it can never be achieved. So his Riemann sum. So this R is to this. I don't see his name. I cannot find his name. I read for you. So this R, why we use R, we want to remember this idea is from Riemann. Okay, so that's his name. We choose this R to represent this Riemann sum. This whole idea is his idea. Yeah, Riemann sum, right? All right. So that's why we use R. So Rn, right? If we want to cut the pieces into n pieces, we call n. If we want to cut into k pieces, we call rk. So the width, so you see each rectangle has width 1 over n, right? But the y value is different. The y value is, this is f of 1 over n, f of 2 over n, f of 3 over n, f of 1, or f of n over n. So we add all these up. So 1 over n is a common factor. Then we see each one has 1 over n squared. So we factor out 1 over n cubed. Then we left with the numerators, 1 squared plus 2 squared plus 3 squared up to n squared. If you remember this, this has a formula. So this has a formula. From 1 square adds up to n squared, so the counting number, right? 1, 2, 3. It's consecutive counting numbers. So 1 square adds up to n squared. It has a formula. It's 1 over 6 n times n plus 1 times 2n plus 1. So let's substitute this. So r over rn cut into n pieces. In the end, we get this n plus 1 times 2n plus 1 divided by 6n squared. Now, we want to take a limit of this. Let n run to infinity. Right? You can look at this. This is a function of n, right? So Rn is a function of n. So we can take a limit. So we take a limit, let n run into infinity. That means we are cutting this piece infinitely many pieces. We know that how do we take this? We have rational functions, right? We have polynomial in the numerator, polynomial in the denominator. We apply ignore rule. Right? We apply ignore rule. We say, okay, take the leading term. So n times 2n. We have 2n squared as a leading term in the numerator. Denominator 6n squared. So we ignore, we take so we have 2n squared divided by 6n squared, that is 1 over 3. The limit of 1 over 3 is 1 over 3, right? So the exact area of this is 1 over 3. You see the marvelous idea about the limits, taking limits? Right, you cut it more precise, more precise, more precise, so we could see this evaluation, like getting closer and closer and closer to 1 over 3. And it's exactly 1 over 3. So this is the idea of Riemann sum, all right? The Riemann sum we can cut, we can cut into many pieces. And also we're free to choose the y value. We could choose the left point, right, as y value. We could choose the right point as y value, or sometimes we choose the middle point for the y value to approximate the triangles. Okay, let's see this definition. The area A of a region S that lies under the graph of a continuous function f is the limit of the sum of the area of approximating rectangles. All right. So the area is, we're taking limit, we let n run to infinity, right? To have this. So this is to show, right? We can approximate the y value, the height of the rectangle, choose the middle point of this rectangle. So this x value, right? We could choose this x value, so on and so forth. And the finite sum, we use sigma notation. So when we talk about finite sum, we use sigma notation. Oh, sorry, we're out of time. Okay, we'll talk about this next time. All right, thank you, Amir. Yeah, I have another class to go. Okay, thank you, guys. See you next class. See you on Thursday. Thank you, Amir, for reminding me. Sometimes I just, forget. Thank you.